going to go ahead and share my screen. Wonderful. Is everybody able to see sort of this IDE on the left and then this web page on the right?
Yeah.
Wonderful. And is this too small or should I make it bigger?
Bigger will be better.
Got it. Okay, let's do that. All right. Is that a little bit better?
Yeah.
Yes.
Okay, wonderful. And same with the right side, make this a bit bigger as well, yes? Okay, perfect. So what I'm going to do today is take you guys through the software that we have been building really over the course of the last 10, 12 years. So Simudyne originated as a consulting company that focused on delivering agent-based solutions to a wide range of industries. So we originated working with healthcare. We did some simulations for Apple and Microsoft, and for some sort of globally systemically important banks. And after about 10, 15 years of building these simulations at Hey, can everyone hear me all right?
Now, yes. Now
Okay, apologies. I was muted. Okay. So where did I get cut off? Right at the beginning?
Right.
Can everyone hear me all right?
Right,
Yeah.
right.
Okay, excellent. So effectively, we built Simudyne because we believed that there was currently a need for using agent-based modeling in the financial sector. So following the 2008 crisis, which effectively caused the collapse of the housing market in the United States and a huge propagation of default across the network, there was sort of this move towards risk modeling 3.0 is what we call it, right? Which is this new way of assessing risk, especially in the financial sector, looking at contagions, looking at network effects, how behaviors can potentially impact financial vulnerability. So all of these are the types of things that traditional statistical methods like DSGE models are not able to capture. So they can't look at those feedback loops, which I'm sure as a group of agent-based modelers, you're all well aware of that. So what we did was we set out to build a software development kit. So a piece of technology catered towards finance. So what I want to do today is really take you guys through the software that we've built, give you a small demonstration of how it works and what it does. And we likely won't have time to go into use cases, but also at the end of this, offer anybody who's interested a free license to play with the software themselves, and use it for your intents and purposes if you find it interesting at the end of this. So I'm just going to direct your attention right here on the right-hand side. So I just want to sort of provide us with a bit of a visual image of what the software development kit is capable of doing. So our software development kit is built in Scala, which is exposed by a set of Java APIs. So as a modeler, you will be building your models in Java. So what I wanted to just highlight here is really what the entire Simudyne SDK encompasses. So we're able to ingest and output data in really most of the most popular kind of data file formats that we see in the market today. So you can, if you're using a very large HDFS, Hadoop distributed file system, you might want to use a file format like Parquet. So we support that type of technology as well. We also support the generic sort of CSV, JSON, SQL, Hive, and H2. So you can just hook up your simulation to a JDBC source and start to pull in and dump data that way. It will automatically dump the agents, the state of the agents, the network at every step. So it makes it very easy to sort of input and output data. We have this core engine that's built in Java and Scala, and you can manage that project via a dependency manager like Maven or SBT. And we've really got a core set of functionalities and features that the Simudyne core engine handles. So you're able to scale your models, distribute those models for your Monte Carlo simulations, and really build out a full tested and version controlled bit of software, an application with our toolkit that can be managed at an enterprise scale. So when we say enterprise scale, what we're really talking about is a piece of software that leverages the infrastructure that major banks and financial institutions, and really a lot of most industries, are investing in today. So some of the technologies are like Cloudera or Red Hat, OpenShift, even just Hadoop, right, is being leveraged within most large organizations for their data processing, right, and for their machine learning workflows. And so what we've done is we've built this simulation platform that sits on top of that infrastructure. So you're able to deploy it in a container, you're able to deploy it across a Hadoop cluster, and then you're able to run your models by distributing them by either using Spark, if you want to go ahead and just set up a bunch of Monte Carlo simulations. You can distribute those across a Spark cluster and really rapidly increase the speed of your computation. The other reason why we've decided to actually build this to be distributable via Spark is because in a lot of organizations, to support a very compute-heavy agent-based application, sometimes you have to buy custom hardware, right, that has a lot of RAM, or it has a lot of cores, CPU power. And so instead of forcing these organizations to increase their permanent investment in compute, they can leverage what they've already invested in, so the infrastructure that they've already spent money on. So the reason why I'm sort of going through this level of detail is because it has been a driving force in how we've actually decided to design the agent-based toolkit. So you can distribute your Monte Carlos using Spark, or we have another bit of technology called Akka that we use to actually distribute the model horizontally. So you could scale your model up to hundreds of millions, billions of agents, and then actually scale that across a cluster using Akka. So Akka is a message passing framework, if you're aware of it, that allows us to just effectively divide up the computation across a massive cluster of nodes. So that allows you to scale up a simulation to millions, hundreds of millions, billions of agents, and just distribute that across a cluster. So that's just what I wanted to talk about there. Any questions around, any questions around sort of the tech stack and how we sort of view everything?
Do you have manual?
Yes, yes. So this page right here is actually in our documentation. So if you go to docs.simudyne.com, we have an open and public documentation, which I will try to put in the chat right now, if I can. Let me see. Oh, maybe I won't be able to see the chat. Oh, here we go. Perfect. So we, and everyone's still able to see the coding environment and the web page, correct?
Yes.
Okay, excellent. So we have a documentation. If you go to docs.simudyne.com, You can see everything that's within the SDK. So on this main page, we have some tutorials. We have a breakdown of the features here that you're seeing. We have some sample models that are more representative of the larger scale enterprise simulations that we build for some of our customers, or excuse me, our customers build in our software. We also have a very extensive reference documentation. So this will take you through all of the various features, how we actually create agents, how we go about connecting some of our agents, and how we set up communication between those agents. So all of that is here and available to you. If you just if you follow that link, you'll be able to see everything within the documentation. So what I'm going to do is I'm going to actually now switch over to our integrated development environment. I'm going to expand this window just a little bit. So really, the Simudyne SDK is built for rapid prototyping and for ease of scaling. So what that means is that we have abstracted away the very tough computer science challenges that go with building these agent-based simulations at scale. So when we're simulating, let's say, as an example, the housing market here in the UK, when we want to simulate all 27 million households, we can build a model of 10,000 households, and without changing a line of code, we can scale that to 27 million by using the back-end distribution, which the modeler never has to interact with. So the Simudyne SDK, our bit of technology, is really just a set of functionalities and libraries that make building an agent-based model far simpler. So what a project in our SDK looks like a very common Java project. So if you've ever come across any sort of Java development, a lot of this will look very familiar to you. So what we wanted to do was create this software development kit that focused on best practices in software development. So there's unit testing, version controlling. You can really manage it just like any other software application. And so what we do is we first define what we call our main model class. So I am currently in this main Java class, and this is where we define all of the really essential components of our agent-based simulation. So the first thing we do here is we are inheriting an abstract class, which comes from our toolkit called an agent-based model. So this contains all of the features and the functionality to define the environment, where the agents exist, what behaviors and initial parameters the agents will start with. We also define what we call the global state. So these are going to be parameters in our system that we want all of our agents in the system to have access to. So what I want to do is to just give this a little bit of life. What we've built here is a very simple demonstration of a mortgage market. So what we have is we have a bank and we have a group of households. The households are a heterogeneous population where we've used some real income data from the UK to create a somewhat realistic population of households. All of those households will be interested in getting a mortgage from the bank, and the bank will be making decisions about whether they want to approve or reject those mortgage applications. So this is a very simple toy model where we've just broken this down to make it very easy to sort of understand what's happening within the SDK. So I'm actually going to go ahead and just compile my project. And the moment we compile it, oh, let me drop this. Apologies, something got changed. Cool. Doing a bit of live coding. There we go. Okay, so this should compile no problem. Models trading. Add import. Cool. Okay, so what should happen now is we should just go ahead and compile our model. Our SDK also comes with a built-in console for ease of visualization and for debugging and investigating your models at a high level. So there's two ways to run your simulation with our software. One is to use the out-of-the-box console, which I'm going to show you in a second. The other option is to use, you can completely bypass this console layer, and you can either run it headless, so you can run your simulations without any sort of visualization and just dump your data and pull that into a data science workflow of your choice. Or you can actually connect the SDK via a set of REST APIs to a bespoke console that you've designed for a particular purpose, or it can also just, using the REST service, be hooked up to something like Power BI, another tool like that. So what I've done is I've compiled the model. So I've compiled the simulation, and it's provided me with a local port where I'm going to be able to actually pull up my console. So this is our out-of-the-box simulation console. I haven't done anything yet, so we haven't run any simulations as of yet. But now that we have this console up, I'm just going to walk you through a little bit of how we actually put some of this stuff in the console and generate it. So here are where we store a lot of our input parameters. We tag them with a quick Java annotation. When we use a Java annotation here, what it does is it actually causes these to appear right here. So if you want to add any input parameters and want to be able to modify them from this console, it's very easy to just put up new input parameters. You define a field and tag it with the annotation, and it's going to show up on the left here in your inputs. The next thing I want to do before we jump back into this console is just quickly describe what we call really the two main methods that are executed within every agent-based simulation within our SDK. So a lot of these are very common across agent-based modeling, but the very first thing that we do is what we call the setup. So that's where we are right here in this method. In the setup, we define the agents that we want to generate in our simulation, and then we connect them in some meaningful manner. So the setup is what generates our environment. The next thing that happens is what we call the step. And this is the logical sequence of behaviors that we expect to be executed at every time step. So what I'm going to do is I'm going to hit this initialize button. When I hit the initialize button, it is going to be executing this step method. So this step method calls on some of our built-in functionality like groups, which allow us to generate a population of a type of agent. It's also going to be calling on some of our built-in graph generation algorithms. So the SDK actually has a whole host of built-in graph generation algorithms that allow you to quickly build very complex networks that are representative of the types of networks that we build within many agent-based applications. So when I hit initialize, what's going to happen is we're going to see some tiles generated here. All I've done so far is generated a group of agents, given them each an income and a wealth, and I've connected them in some way. So what I'm going to do, we're going to switch to the network view. And here we're able to see what our environment looks like. So in the center, we have a bank. And around the edges, we have a population of households. So each of these households has their own unique income. For the sake of the demonstration, we've just all started them with a static wealth parameter. And so this is our environment. Now that we've sort of seen our environment, we're actually ready to go ahead and run our simulation. So I'm going to go back into our graph view. And what we're going to see is we're exposing some of the dynamics of our simulation. So when we use this simulation particularly, we're looking at it from the perspective of the bank. So we want to look at this as if we are the bank in the center of this network view. And around us are a population of households who are interested in taking out a mortgage with us. So at every step, households will decide to buy a house, and that behavior is governed by an action. So here is a very simple action where a household makes a decision about trying to purchase a house. The next thing that happens after every household has decided to take out a mortgage or that they want to take out a mortgage, they will send a message to the bank. The bank will receive the message, make a decision about whether they want to process that mortgage application or not. And then they will send back to the households their decision. So we have this little bit of communication that happens here. And then afterwards, we have what we model as the normal behavior of both the household and the bank. So our households will potentially incur an income shock. They will earn their income, pay their tax, go through what every household would likely go through. And same, the bank is going to accumulate income, process any arrears, and deal with some mortgages. So let's go ahead and run this simulation. I'm conscious we're running out of time here. So I'm going to just step my model forward for 100 steps. So we've just simulated 100 months of interaction between the household and the bank. And immediately we're going to notice we're able to track things like the number of mortgages being taken out. We're also looking at, what are the number of bad loans that might be occurring. We're also tracking the assets at the bank and the impairments. So as a bank, when I am looking at my mortgage portfolio and trying to understand, one, how does my mortgage portfolio behave under certain conditions? Having this type of dashboard or agent-based environment where I can quickly test scenarios and understand the impact of potentially an exogenous shock scenario, like currently in the UK, we're dealing with Brexit, right, which has had huge impacts on the financial sector. All of these can start to be investigated at this level. So I'm just going to run one really quick scenario so you can see a little bit of what that actually looks like. So I'm going to stop my simulation, and I'm actually going to just change this income volatility parameter, which just is going to shock the income of the agents in a stochastic manner. So I'm going to go ahead and initialize my simulation again. What I've done is I've stopped it, changed an input parameter, and now I've reinitialized. So when we talk about rapid prototyping and testing, you don't have to go back into your code, change the parameter, recompile, and then run it again to get the console. We can just start to test very quickly from this layer. So now I'm going to rerun my simulation, and we're going to see some very different results. Immediately, there's a far less number of mortgages that are generated. The incomes are drastically impaired. Here you'll notice that we have an increase in the number of bad loans, an increase in the number of impairments and write-offs. So you can imagine as a bank, when I want to understand what might potentially happen to my mortgage portfolio, should we have these very large systemic shocks occur, it's very difficult to do that with other traditional statistical methods. So by having this agent-based environment that you can build on your desktop, then scale up and just deploy across a Hadoop cluster and really integrate into your existing data science workflows, this becomes really a function within the organization. So our goal is to create software that can actually be used at large scale enterprise environments where tier 1 banks, starting here in the UK, can actually create an agent-based simulation function within their organization. So I'll pause there because I know I went for 25 minutes and see if there's any questions.